Great. Next up, I'd like to introduce Peilong Lee with Sparkling and
Thank you for Paco's instruction. It has been a great experience learning and researching Spark during the last half year. I found there are many advantages of Spark over other cluster computing systems. However, I also find there are some points that Spark need to be improved. Dear ladies and gentlemen, today I'm going to talk about our Sparkling project, identification of task skew and the speculative partition of data for Spark applications. This is a joint work by 2 universities. My name is Peilong Lee. I come from UMass Lowell. And we also have Xiaobing and Dr. Tian Zhao from University of Wisconsin, Milwaukee, and also Dr. Yan Luo and Dr. Yu Cao from UMass Lowell. Okay. We all know that Spark has provided web UI and other instrumentation tools such as Ganglia for users to better understand the performance of their application. However, the more I use those tools, the more I found why it's not providing the information about why an application does not yield expected performance. Instead, our Sparkling Web tool provides better execution. Oops. And sorry. Oops. It happens. Okay. Sparkling Web tool provides better execution visualization, as you can see in the later slides. And also it provides an in-depth statistical analysis. I also find Spark may generate unbalanced tasks during doing the partitioning, which we call them data or computational skew. So in order to solve that problem, we have proposed 2 partitioning methods, one called decremented partitioning and the other called application-aware partitioning. So during the rest of the presentation, I'd like to divide the content into 2 parts. Part 1, I want to talk about the Sparkling Web tool, and in the second part, I want to talk about how we mitigate data skew in our own Spark application. So first thing first, Sparkling Web tool enhances Spark application development in the following ways. First, it provides a more detailed metric system, and then it provides a task view and executor view to help understand the performance. And also, it provides overall performance with in-depth statistical analysis. And fourth, it had helped programmers to help avoid the data skew and also the small tasks. This is how Sparkling Web tool looks like. And if you are interested, you can check out our demo page for the Spark Summit. It is pr01.uml.edu. And if you click the very first button on the web tool, on the menu bar, you can go into the task timeline view. You will get an annotation bar showing the meaning of y-axis, which is task ID in this case, and the meaning of x-axis, which is time in seconds in this case. And also, it shows different colors with different meanings. For example, the blue bar stands for the deserialization stage in a task, and red bar stands for execution stage. And also at the last, you can see a total duration time showing the overall execution time for this current application. This timeline view shows the detailed information about how does an application performs on a task basis. From this view, we can easily see the transition between each RDD stages, and we can catch those tasks that has slowed down the whole application. And if you continue to click on the second button on the menu bar, you will go to the Executor Timeline view. In this view, we can also get a similar annotation bar showing the meaning of y-axis, which is executor ID in this case, and also the meaning of x-axis, which is time in second. And also, we can have some blue bars with numbers on it. That's the task ID. So basically, from this view, we can see the different tasks running on different executors. And we can easily see there are some short-living tasks like this, and also some very long-living tasks like these guys. And if you look into each horizontal line, which is the executor, you can also find there are some white spaces. That's the time during which the executor is idle, and that's the time we want to take full utilization of. Okay, if you go to the second button on the menu bar, you will get into the statistical analysis view. In this page, we can see there are in contrast with Spark Web UI, the table showing above provide an in-depth analysis on statistical properties of the application behavior. We can see we provide the maximum time and minimum time, average time, standard deviations on different stages, and also the scalar delay. And we also find that small tasks or empty tasks may introduce a high overhead to our Spark applications. So basically, we want to know how many percentage of small tasks exist in our application. So we provide this view to simply show the percentage of the small tasks. And also, we found histogram might be very useful for Spark developer to know the distribution of a target. So we provide 4 options for different stages, and also the scalar delay histogram. It's very interesting showing in this picture that we can see there's a high percent of tasks, almost 300 or something, showing the execution time of almost 0. And thus we call them the empty or small tasks. And we can also find there are some tasks that has execution time way much longer than the other, or the average tasks. That could introduce the task skew. Okay, in the second part, I'm going to talk about how to mitigate the data skew in our own Spark applications. We know that Spark has provided a speculative mechanism which can handle the stragglers, AKA the slow node. But there are a lot of other applications like biomedical multimedia processing applications we use is it can generate a very high computational skew. I'm keeping talking about the computational skew or data skew, so where it comes from. Spark has provided the partitioning method which will divide the workload into slices with equal head count. But the problem is, what if there are unbalanced workload on each slice? And of course, that's what we call the data skew comes from. And so to tackle with this issue, we propose two methods, partitioning method to mitigate data skew. What you can see here is a problematic partitioning. We know the next stage will only start from the end of this longest task. So basically, this period of time is wasted for your application. So the first way we do it, we call it decremented workload. We know that the start time of the longest task often determines whether there is any idle time between stages or not. So basically, we want the task that has been issued early have the heavier workload than the later ones. In that way, we will have less time being wasted. And the second way we do it is partitioning the RDD with domain knowledge. If with domain knowledge, we can make sure that each slice will contain almost similar computation complexity. So in this way, we will do the partitioning more wisely. You can see if we have the domain knowledge, we can know that this task might be the TAF might contain the TAF data. So we can partition the RDD into this way, which will have the stage execution time being shorted. So our test benchmark is the PPR benchmark. If you are interested, we have a paper publishing for PPR. You can check out the link, the reference below. And for a quick introduction to the PPR benchmark, we have image query and transmedia query applications, which contains SIFT and LDA algorithms. And the data set we use is Expedia articles, which contains 2,866 multimedia documents, including images and texts. And the domain knowledge we use for this case is edge pixel percentage, which is showing in the algorithm here. It equals to the number of edge pixels divided by the total number of pixels. Why we use this as a domain knowledge, you might ask. So first, it's very lightweighted, and also the image or image transmitter query application use local features. So edge pixel percentage is a very good stand for local feature complexity. That's why we use it. And in this slide, I'm showing the experiment result of using our own partitioning method. So on the very left vertical bars, you can see here is the Spark naive partitioning method, which has been normalized to 0 or to 1. And what you can see here is the hand-modified partitioning. The meaning for this hand-modified partitioning is this partitioning is obtained by trial and error. So you can simply treat it as the ideal way of no data skew exists. So if without data skew, we can see the performance is lower, which has probably 23 or 28% reduction. And the second column here is by using the decremented partitioning method. And you can see here, it shows a slight improvement on this in this case. And if you're using the domain knowledge partitioning, you will get better performance. The best case is 11% of improvement. But you might see this improvement is too little, and you might want to ignore it. But in this case, we are using a very small Wikipedia data set. So if you want to try a larger data set, you probably have better performance, better than this. And I want to quickly go to the conclusion because my presentation is 15 minutes in total. And so the Sparkling Web tool provides more insight for developers on how to improve application performance by decreasing data skew and small tasks. And also our proposed automatic data skew mitigation algorithm shows a 11% increase of performance on our own biomedical benchmarks. So that's pretty much for today. And if you have any questions, I'm open for any questions. Yeah?
Yeah, for the decremented partitioning, how do you actually figure out which one is going to run longer without running it?
We will know which task could be issued earlier than others. So for the early task, we have a list of all the tasks with different workload. So for the early issued task, we want the heavier workload task being running on that task.
But how do you know which is heavier? So in your Wikipedia example, let's say I'm extracting n-grams, right? How do I know which partition of the Wikipedia dump is going to generate more n-grams than any one?
I understand your question. So you are saying how I know which task going to be heavier than others. We have do a profiling before running all the applications. So that's why we use edge pixel percentage as the domain knowledge. We run the profiling first, and we find which data might be tough data for our application. And we group that data into the heavier workload task group.
So maybe this is a dumb question, but wouldn't the profiling take up just as much time or more as simply running it?
In our case, in our experiment, we have doing an extra stage doing the profiling. So the profiling stage takes like 2% of the total execution time. So basically, you can overlook that part of overhead. Yeah, thank you. Yes, please.
Is there a way that we can use the existing or the visualizations that you were talking about our existing stuff?
We are working towards to open source this software if you are interested, but currently we are under beta development and we are not our alpha development, and it's not open for other developers to use. But we definitely want to make it open source, and I hope in this month we probably have it for others to use. Yeah. Yeah.
This is a deployment work. You have to deploy on every node, or for profiling, you have to deploy any plugin or anything on every node.
Yes, it's similar as the other algorithm you run on Spark. It's like you're doing an actual stage to do the profiling with domain knowledge you want to use.
Okay, so you basically submit your jar along with your job for profiling, or you have to install your plugin before you submit it?
Yes, that's the way we do it. Yes, please.
Based on your approach, is it possible your profiling result is different from what really happened? Assuming you have a 5 text, their profiling result might have a rank from 1 to 5. But when you really do wrong, maybe they got different order because of the profiling function, the sample answer, right? So in that case, your method probably completely screw up, right?
I didn't really get your point.
How can you make sure the heavy test based on your profiling result will really happen when you really run the full set of the data?
Okay, so the domain knowledge really matters for this use case. If you have like stupidly choosing other domain knowledge like we previously do, And yeah, you can get like worse performance. Yes.
So you imply your sampling method when you're choosing the profile are very important for modeling.
Yeah, you have to very cautiously choosing your domain knowledge to do the profiling. Yeah.
Thank you very much.
Thank you.